don't worry, is it correct or not. So any question will make things more clearer. So therefore, this is originally you have a U is a label and P is just a due. And now we completely transfer the minimization to the due. You have a P1 is a vector, P2 is a vector, you have n vectors. You minimize this one, assume you have a minimizer, like P star with the optimal minimizer. And the previous one, so here you have each point you have n numbers. We assuming only one of them is the smallest. And then this will give you a unique label, and then we can prove this is correct, and this one is a unique global minimizer for the original the relaxed model. So therefore, you also get is a global minimizer for the original pulse model. So this you assume those n numbers, only one of them is smallest. And then the next question that in practice, you see when we compute many images, normally just one of them is smallest. We always get a unique UI. So all the computation we have done for all the applications we have done, there's always unique. But theoretically, you see, if two of them are smallest, you see, every point you have two. If two of them are smallest, and this happen in a region, in this case, we can still, you see, that the one way, like he said, you can take, you see, two of smallest, you take a half here, take a half. That's one way. But if this happens, I think we can threshold. We get a minimizer. You get threshold. I think still in this case, if two of them are still smallest, we can still guarantee there exists an optimal binary variable U such that this is a U is a binary such that this is still one of the global minimizer. We can still guarantee if two of them are smallest. If three, we don't have a proof. If more than two, we don't have a proof. But for practical images, we never observe you get, we always have one is the smallest. You always have one is the smallest. And then always you get unique UK. You see which one is the class K if the case number is smallest. We just solved this problem.
Why do you think you don't have a result for the case more than two?
You mean there are more than two? It's not easy to prove. For two, theoretically it's not easy to prove. Also in that case, you see it could be this region, only one of them smallest. Another region, two of them smallest. Another region, three of them are smallest. So those three regions, they can even touch to each other, and then it's getting very complicated. So we believe you can prove for general cases. Even we were trying to give a proof, but later we found that proof is not correct. So, but luckily in practice, always one of them is smallest. So you always have a unique label. Yeah. So what we do in practice, we just solve this problem. And then you have a mean. You see, mean is non-differentiable, and then we do a smoothing. On that one. Yeah, so here, you see the analysis were given here. We also use somewhere here. Here is a list. So the PDF file for the talk, in the end, I will do more editing, and then I will pass it to Professor Lee, because you see still many typos now. So after lecture, I found the typo corrected. So after lecture, I will give everything to Professor Lee, so you can get from him. I can also put it into my web page. If you send an email, I will tell you a link. You can click. Maybe I can set a password. Also, I can put the related papers, like the well-known Chang Wei paper, other paper. I can also put it there, so it will be easier for you to download. Because mostly when I talk about those papers, you just talk about idea. In the paper, there are a lot of other details. When we talk about those papers, we just talk about overall idea. But if you still look back into the paper. So here, I think if you see here, we can handle arbitrary n phases. If you just have one phase and then you just have a U1, U2, then it was reduced to something very similar to the Nikolova thing. To use the characteristic functions, and those there's a number of people who have been also trying to use the characteristics. But you see, no one has proven. You see, as what we did, you guarantee that's a global minimizer. You observe this primordial relationship. So what I'm talking exactly before here, That was we did in this paper. But those other paper, they also using the characteristics, use some kind of truncation, but never in the sense we did. So I'm listing using nearly all the papers in this area. So I will give this to you later. So give this to you. So what we compute essentially, you see here you have a mean. This is not differentiable. We want to smooth it. We use such a kind of a smoothing. So if you have UJ numbers, you put the S here. When S goes to 0, and this function go to the minimizer of this one. So this is essentially, I think, so therefore you see we want to minimize this one, and then we just put UJ set, and then this is you get S. So and then you become, this is smooth minimization. This is smooth minimization. So essentially we replace this non-smooth problem by something smooth but related to a small parameter S. Small parameter S. This is standard smoothing. You see the minimize of n numbers essentially is an absolute value. You smooth the absolute value, and then you get a minimizer of n number. We do such a smoothing, and then you see we solve the smooth problem, and check that the smooth problem give you P1, P2. But one weak point is this algorithm, the memory is very high. If you want to segment into n phases, so how many functions you need to compute? Each PI has a P1, P2. You have a 2n function to compute. Sorry? Yeah, you have a 2n function to compute. And that's one weak point of this method. But even though we have been using this method to compute phases up to 128, so that means you compute several hundred functions. But luckily, mostly these normally take about 30, 50 iterations, and that's already enough. So normally you don't need to do many iterations. So that means the computational cost is not very high, but then the memory cost is very high. You need to memorize all those functions, and you need to compute. So essentially, you see each P1 has each PI has a first component, second component. Those two components summed together should less than 1. Should be less than 1. So therefore we smooth it, and then we do a projection. We do a smoothing and do a projection. That's what we compute. So this analyze, you see originally you have a P, here you have a smoothing P. We analyze, you see the minimizer of this one when S goes to 0, and these differences go to 0. So therefore you can guarantee the smoothing is close to the original one. And the computation is very cheap. Computation is very cheap. So essentially, so here is a projection into the unit ball at every point. It's very easy. If it's is outside unit ball, you drag it back. Inside, you don't do anything. So this is a projection. Here you just compute this gradient. Here you use a time step. And this is a computation is nothing, nearly no cost. No cost to do this one. And so therefore you see that you do the projection, you do several iterations. The computation per iteration is a cost very, very low. Normally it takes about not many iterations, 50, even 100 something. But the memory will be high. The memory high only if you have many labels. You see, like a Tom Vesey, maximum you can compute. I have never seen people use a Tom Vesey compute more than using 16 labels. So in this way, you can easily compute 20, 30 labels. There is no problem. But if you want to compute several thousands of labels, and then the memory will become a problem. But otherwise, it's a very low cost. You see, very low cost per iteration, and goes very, very fast. So I'm just talking with Professor Lee. Maybe tomorrow or on Friday, I can transfer some code into the computer. We can do some online demo, so we can show you how quickly you solve the problem.
Tomorrow is Thursday. Tomorrow and Thursday.
Oh, tomorrow and Thursday. Yeah.
Normally, how many iterations you need?
Normally, let me see if I have an iteration number. You see, normally, there may be iteration count. For difficult image, several hundred. For easy image, about 50 50, 80 should be enough. So the computing cost is very, very low, very low, right? And then we compare with you always you see your method is good. We compare with some of the existing ones. We compare with the split Bergen, with the ZAC.
And also, how do you set the initial?
Initial, so P can be anything. P is a dual variable. P is you can just start with a 0. All of them are 0, and from 0 you do the iteration.
Have any modification for the initial data?
Because it's convex. So it's a convex. So whenever you start, for most of those tests, there's a unique minimizer. So no matter where you start, you always end up at the same point. So therefore, it doesn't depend on the initial value. Yeah. Here is the input image. Here is a ground truth. Here is by the alpha expansion. Here is just by alpha beta swap. Here is by the Lellman threshold. They have another threshold, and this is produced by our methods. And this is 32 by 32. I don't know how many iterations. And this is the input. Again, the same kind of experiment. So this is by our. And this even we can do online because MATLAB. I have a MATLAB in my laptop. By the license lies in Norway. So I must do a VPN connection to run. So therefore, yeah, here is essentially we try to compare the image. You see, if one of them is smallest, you can guarantee that's a global minimizer. So I think for this one, you see all the different methods produce essentially the same. All of them produce the smallest image. I think this is maybe one for the triple junction, and we cannot guarantee one of them is smallest. And then we just try to show you see our methods always produce the smallest. I think our method must be this curve, always produce the smallest image. This is a try. We have computed many. The power is it's running out of power now. Okay, no, it's okay. Yeah, no, it's okay. So here are some more tests. So here is a test. I think this is we segmented into. I think it's about maybe 10 around 10 phases. You got 1, 2, 3, 4, 5, 6. So there's around 10 phases. So how many phases you tell the code in advance? N you see. I say 10 or 15, and that's you set it, and you compute. So again, I think that's the alpha expansion. So this is the 4 neighbor, that's 8 neighbor, and this is a POC, and this is our methods. This is our methods. Mm-hmm.
And this is a global minimum.
It's a global minimum. It's a global minimizer. So we compute the P, and from P we get the labels. And so always we check, you see that if there are 2 is the smallest. In real computation, it seems always one of them is smallest, and then you always have a unique label. So never happen. Here is a synthetic image. For this synthetic image, theoretically, you see you can get. So here is a 3 phase. So n equal to 3. You can for this one, you see. Away from this boundary, you see those regions, you can always, there's 3 of them are the same. So in this case, you don't have a unique minimizer. But then, you see, this case is that here we have a region. Outside the region, I have 3 labels. But inside this region, I don't know what's a label. And then I ask the label on the boundary must be the same. Inside, I should segmentate this region into 3 regions such that the length of the interface is minimized. And there's a theorem by Mumford with another person, shows that such a kind of a minimum length shows that it must be triple junction. If you should minimize the length, you should always maximum triple junction. You cannot have a four junctions. That does not minimize length. And the triple junction that here must be 120 degrees if it should minimize the length. So therefore, this is a good test that your code found the global minimizer or not. If your code does not get 120 degree, if your code gets, you see, more than triple junctions, that's clearly not the global minimizer. So this is a test. This is your alpha expansion doesn't work. You get this region wrong. And B is Lehman, so they have approach works. And so I think this is our method. We get it 120. Here there's some kind of, you need to do a proper threshold. If you don't do proper, it doesn't work. So this is, if you read other papers, who is using this example as a testing example. So those are the tricks. Just test, you get a global minimizer or not. If a global minimizer, it must be 120 degrees. It must be triple junction. But even for this problem is easier because the global minimizer, this is the global minimizer. There's a unique global minimizer. There's another test that you have 4 faces. If you have 4 faces, so here you have the region. Here you see, here you have a region 1, 2, 3, 4, and then you just still take a circle away. You ask to segment this region into 4 faces such that the minimization is the length is minimized. This problem has 2 solutions. One of the solutions is I think like this way. This one, and then you rotate by 90 degrees. That's another solution. You have 2 global minimizers. And this problem is even harder. So therefore, you see, once you pass this test, you can test on this problem. That's 4 phases. You can 5 phases. You can even have 3 global minimizers. So therefore, you see that when your code is developing more and more stable, you can testing on those synthetic images, which are more and more difficult. And that's really a test to see your code works with the global minimizer or not.
So,
yes.
Just let me check. I am following you one.
Right.
So A is input. So A is input image.
No, A is an image such that inside here I don't know what's a label.
Yeah.
But I should get a label inside here such that the interface inside this circle is minimized.
Yes.
The length is minimized.
Usually there are so many kinds of ground truth image.
There's only one ground truth for this problem.
Because the inside of the circle we don't know yet. But
that's right.
In your consideration, because you are trying to minimize the energy, also the length.
Here I take away the energy, only the length term. Only the length term. So essentially Fi equal to 0. So this is just testing on the code. So this is not a real application. Fi equal to 0 everywhere. Only minimize the length. And then this is a global minimizer. And this is a unique global minimizer. If you put Fi, that's different. Mostly, if you put Fi, that makes the problem easier to solve. Yeah, very good. Yeah, very good. And so there, this is, yeah?
Actually, in this algorithm, you want to get the unknown part in the image, right? Because your input image, some part is missing.
Yes.
So in your last image, you get the unknown part, right?
So the problem for this problem is that this part, the label, I don't know. I want to find the label such that on the boundary, it takes the known labels. Inside, I don't know what you should take, but you should minimize the length of the interface.
So have you ever tried to apply this algorithm to like input?
Yeah, you can definitely. So this is some kind of imprinting. You imprint the label. But the real purpose of this test is that because for this one, I know the global minimizer, this is a unique global minimizer. So to test your code works or not. Many code doesn't pass this test. Many algorithms in the literature, if you put on this algorithm, it doesn't work.
To my opinion, if try to use in painting, but then the B is more natural. If you try to use this method to in painting,
that's why it could be, yeah. But here we are not doing in painting. In fact, we just want to minimize the length. We must have a clear partition. You must give me a clear partition. This one, you see, for this region, is difficult to decide which class you should belong to. Right? Yeah. Yeah. So I think also here should be CVPR, no CVPT. There was also some more related work here. In fact, I'm going to talk about those ones. I'm going to talk about this one. Okay, so now we finished so now we have talked about snake, level set, piecewise constant level set, characteristic functions. And now we should talk about one more approach to solve it, to graph cut. So essentially, you see a labeling problem, as we said, is a combinatorial. So combinatorial means you only have a finite number of solutions, you combine them together. So graph cut is essentially one of the ways to solve a combinatorial. So here we don't turn into continuous minimization. We just do it over a discretized minimization. So graph cut is one of the methods to solve those kind of things. And this is also guarantees global minimization. So how do you graph cut? So you see in the two-phase term, we say if you use the level set, you put the level set here and C1, C2. There's another way. There's another way. Essentially, this is a characteristic. This is a characteristic for region 1. This is a characteristic for region 2, right? So this is a characteristic for region 1. This is a characteristic for region 2. So instead of using, you see, we can use a characteristic phi 0, 1. So here you put the characteristic region 1, here characteristic region 2, here total variation. So this should, this is equal to that one. This is equal to that one. So this is the level set 1. So this is a two-phase, the characteristic one. So what we have been talking is you just relax this one to interval. That's the relaxation methods we were just talking. And the four phase is also you can do the. In fact, this is the four phase. You can also use a binary variable. Let's skip this one. Let's skip this one. We will sometimes come to this one later. All right. Let's also skip this one. We come back. So here, let's go to the graph cut. So graph cut is, you see, is a computer science people all knows about it. So assume you have, you see, this is a graph. A graph have many nodes. You have many nodes. There's a connection between the nodes. You can think, you see, this is like an internet. This is one of the servers, and the servers are connected together. From this server to this server, there is a connection. You can have a reverse direction. So each connection, there is a capacity. So what's the maximum amount of information you can send? And so here, and then you get a computer network. You can take two nodes. So here is a source, here is a sink. So and then there is one of the questions is a so-called is a cut. So therefore, a cut is such a thing. Here, the red line is a cut. A cut is that you separate the graph into two parts. One part, everyone is connected to source. Another part, everyone is connected to the thing. And this will be called a cut of such a graph. And the cost of the cut is a capacity. It's a summing of, there is a cutting edge. So this one here, those are the edges between the two parts. So the cost is the sum of all the capacity here. If this graph have two directions, you are allowed only to cut one direction. You can also cut both directions. So this is called the cost of a cut. And so therefore, the minimum cut is found the cost which have the minimum cost. So there are many different ways to cut this graph. But one of the cut has the smallest cost. The cost of the is this one. And then there is another called the max flow. The max flow is that you found the maximum amount of flow from S to sink. This flow is not computer network. You think this is like a pipelines. So those are the junctions. So this is the pipeline, the direction go here. So here you put water, and you increase the pressure. If you increase the pressure here, here maybe you get more and flows out. You increase. At one point, even you increase the pressure, you doesn't get anything more out. And so that means you have a maximum amount of flow. Maximum. So there are two problems. One is the so-called mean cut problem, and then another one is the called max flow problem. And then those two problems are equivalent. So the max flow equal to the mean cut. And this is very natural to imagine. So you increase the flow here, and then maybe on this pipe is still not full capacity. If you increase again, and some pipe will be full capacity. You increase another get full capacity. You increase another get full capacity. In the end, you see that all the pipelines which are getting full capacity, those are the bottlenecks. And that means you cannot increase the water anymore. But still many other, those pipelines, you still have a capacity. But there is a number of pipelines you don't have a capacity anymore. It's a full capacity. Those capacity are the bottlenecks. It's like in the morning if you drive to the city center, you see where the road has a completely saturated. So therefore you see that this minimum cut must be those cut which has a saturated. And those are the smallest. You cannot increase anymore with other places. So therefore you see a cut must be cut. Those are the bottlenecks. And that's, you see, if you sum together all the flows together, that will be the amount of flow you can push over. So therefore, mean cut equal to a max flow. This is very natural to imagine. So we can use this one for image segmentation. How do you use it? I think the idea existed much earlier. But it was really due to the paper by Boykov and Kolmogorov, which is making this idea very popular for segmentation. In the past 10 years, it has been used for a lot of industrial applications. Mostly it turns out to be faster than the continuous approach. We just take this simple example to explain how to use a graph cut to do segmentation. So assume this is a true signal, and this is a noisy signal. So in this case, we know that C1 is 0, C2 is 1. And so this one is you clearly see that how can you segment into two phases? There must be one, must be two. But how do we use a computer network to segment this one into two phases? And this is the network you can construct. So here you put all the pixels. You add the source here, you add the sink here. So assume this is one cut. If this is a cut, and then if you cut, correspond to this pixel, if you cut this edge, I say this is phase 1. If I cut this one, I say phase 2. Cut this one, those are phase 1, these 2. So in this way, you can give a unique label for all the pixels, which class you belong to. Either cut this one or cut that one. You cannot cut both. You cannot cut both, because if you cut both, this is not connected anywhere. You can only cut one of them. If you cut this one, phase 1. If you cut that one, phase 2. So this is if you do such if you try to push the maximum amount of flow from here to here, and then you will get a cut. This cut will give a unique labeling of all your pixels. So it depends on, you see, either phase 1, either phase 2. So we assume, you see, SP, so that's a capacity. P is P1, 2, 3, 4. So P is so if assume, you see, I know C1, C2. So the capacity here is image minus C1 squared. So this is capacity here. And the capacity here is minus C2. So C1, C2 for this image, we know that C1 equal to 0, C2 equal to 1. And if you give those two capacity, if you do the max flow, what happens if WPQ? So here you also cut those two edges. If I assume here there's no capacity, zero capacity, if you try to push the maximum amount of flow from here to there, what kind of result do you get? This is very simple. So here no capacity, which means there's no flow which are allowed to flow here. And then you try to push the maximum amount of flow from here to there. You see the cost is given is distant to C1 square. The cost in the upper is distant to C2. C1, C2 are known.
Just cutting one?
Yeah, you can only cut one. You cannot cut two because everyone must either connect to here. That's called the cut. Right. The cost of this cut should be, you see, the sum of all the things given here. If you do this right, the mean max flow equal to the mean cut. You see which one is the mean cut. It's very easy in this case. If you do this one, you see there is a mean cut. What kind of mean cut is this one? It's very easy. So it's just a simple threshold. You see, you push the maximum amount of flow because it's not allowed to flow here, so the flow can only go here and down. So therefore, if this is smaller, so therefore you push, and this is saturated. You still have capacity here. So therefore, you see that for this pixel, if it's closer to C1, this will be cut. If it's closer to C2, that will be cut. Right. So which class it belongs to, it depends. You see, this one is closer to C1 or C2. And this is nothing else but the threshold. Right. The threshold is at which constant is the nearest, I go to that constant. Right. So this is nothing else but threshold. Right. So this give you the two classes. But however, if you allow flow here, and then it will be different from the threshold. Yeah. If you allow there is a flow between those two, between the pixels, and then there will not be threshold. Right. So that's assuming you know C1, C2. If you don't know C1, C2, so given C1, C2, use a cut to find the region omega 1, omega 2. And then you see, and then you minimize with C1, C2. You see, minimize C1, C2 is the same as what we talked earlier. You just average the pixel. So and then you do iteration. You do iteration go. So therefore you do such a switching, right? So if you have no flow here, in fact, this one is as simple as the threshold. This one is a simple threshold. So you just decide which constant I'm near. If I'm near, I go there. So each pixel you easily have two classes. And then you update C1 here. If you do such an iteration, so this will be most simple segmentation algorithm. If you want to have so here you only have two classes. If I want to segment into more than two classes, how do you do? So essentially, like this one, I have a C1, C2, C3, C4. I want to segment the pixels into four classes. And then what you do is that you just copy this one 3 times. You add S here, you add the T here, and you push the flow. And so therefore, if for this is just copy, it's just 1 pixel. So if you cut the first edge, I say this is class 1. If I cut the second edge, I say this pixel is class 2. These 2. So here is a 0. So here is a 1. If you cut the third edge, so here is a 2. Here is a 2, and here is a 4. Right. So this is another way to give labels. If you want to have more than 2 classes, you copy your pixel n-1 times, and then which edge is cut, that determines the class. So this is amazing. So this is artificial network. You construct it from your brain. And then you just assign the capacity properly. You do the max flow, and then depends on which one is a cut, uniquely get a label. Right. So this is another quite amazing idea. Quite amazing idea. And so for this case, assuming still there's no flaw between the pixels, if you assuming the cost here is a distance to C1 square, if the cost here is a distance to C0, here is to C1, and here to C2, here to C3. Again, if you don't allow any flaw between the pixels, you push the max flaw, this is still the simple threshold, right? Because you see the flaw can only go here, and the smallest gets saturated, the other will not. The other will not, right? So this is mostly use a graph card for segmentation. It seems very difficult for many people, especially for beginners. But if you look at those images, it makes everything very easy. It's very easy how to use a graph card for image segmentation. You push the flaw, depends on which edge is a cut, and then you get the label for the two cases. You can always guarantee there's a unique cut. You either cut the upper one, lower one, so there's no other way to cut. But for these multi-phases, there's a problem. It could be you see those two, so it could be those two are equal, and this cut you see can really go there and then come back, and then you see for this pixel there are several labels. You have multiple labels. You need proof. You see that this we call that one illegal cut. So if a cut which go here and then turns back and then turns back and then for this pixel you have two labels. So you have two labels for the same pixel, and then you need to mathematically guarantee. You see this kind of multiple label will not happen. We have a proof. There is one way to prove it. You see, it should not happen. You see, one pixel you get more than one label. You always get a unique label. That you can prove if this is a cut, that cut have a higher cost than another cut. So therefore, that cannot be a minimum cut. That cannot be minimum cut. So this is the idea. Yeah, the idea to use a graph cut for multi-phases labels to segment image into more than one regions. You need to assign the capacity properly. In fact, this idea was traced back to the Ishikawa. The Boykov did the two-phase into around 2000. This goes back, and then later Darbon and Segil made a connection between this one, total variation. We also have modified the Ishikawa. We also use this one to. So we observe a connection between this one and the Transversal model and the Mumford-Shah model. So I'm going to show you that if we solve this one, it's exactly minimize a discretized version of the Mumford-Shah. You easily connect to this one. You see the graph card people, they didn't know. But in the next few pages, you can easily see that this is just exactly minimizing the Mumford-Shah, but in a discretized setting. Also, now I'm going to make, you see, that was related to, that was Kim was talking. There's a very clear connection between K-mean and the Mumford-Shah. So essentially, you see, if you look at this, so K-mean is just nothing else, just minimize this one. If you give a CI, if you found omega I, and then you just found, you see, which number you are nearest. If you give omega I, the CI just averaging of the image value in that region. If you're alternating between those two, this is exactly the K-mean. Do you agree? If you give a CI, how do you get omega I? You see from the previous minimum cut, you just which one is the smallest. You have a C1, C2, Cn. Every point, if this is closer to C10, so I will be class 10. Closer C9, that will be class 9. So that's exactly K-mean. K-mean is doing that one. So I give a constant. I just check which constant smallest. I assign me to there. You get a new region. After that one, you average, and you do it alternating between those two. So this is exactly K-mean, right? In other words, you see K-mean and so therefore for people working with discrete mice, if you tell them this is K-mean, mostly they don't believe it. But it's essentially K-mean. So therefore, this make another connection between K-mean and Mumford-Shah. So the piecewise constant Mumford-Shah is essentially you try to minimize U0 minus Cy squared plus alpha, the length. So here is a piecewise constant Mumford-Shah. So therefore, and now you can see if you just take the regularization term away, alternating between those two, that's K-mean. That's K-mean. K-mean is used in many cases.
Which means you take the K equal to N.
Yeah, K equal to N. So N mean instead of K-mean. So here, if you say K-mean mostly means you need to know how many classes. This is where the K-mean name comes from. K is the number of class. Mean is a Ci, take the mean value. I think this is, I don't know. This is now it seems that everything come together. The well-known K-mean clustering is just taking the regularization equal to 0, alternating between those two. That's the well-known K-mean algorithm. That's also Kim was talking, so it was related to somehow to what she was talking. If you just add the regularization term, and then we come to the Mumford-Shah, we come to the Chang-Wei model. Essentially, you see those new models are just adding a regularization term, And
then it means it's very similar to the tessellation.
To
Centroid
tessellation, yeah, somehow. Centroid tessellation is another way to formulate the K-mean. Yeah, if you don't regularize, it's completely reduced to the K-mean. K-mean, so the Mumford-Shah or Chang-Wei it just regularize the K-mean. It's just a regularized K-mean. Yeah.
The Chang-Wei model and K-mean, they depend on the initialization.
That's right.
But the graph cut does not.
Graph cut, if a Ci is known, it does not depend on initialization. If a Ci is unknown, you still. So therefore, if a Ci is known, graph cut, this does not depend on the regularization. Does not depend on initialization.
Graph cut also depends on the initialization.
No, graph cut need to assume Ci is known. Yeah. So Ci is known, and this is non-convex, but graph cut still get a global minimizer. So K-mean is also NP-hard. NP-hard, that's due to you have a Ci. If you assume Ci is known, it's not NP-hard. All right, due to this alternating.
So you have a proof on that?
Proof what?
K-mean algorithm is equivalent to.
No, that was just from the from what So therefore, if you alternate. If a Ci is known, you do omega I. If omega I known, you do Ci. That exactly is a K-mean, right? Because if a Ci is known, just from the graph cut thing, that how do you get omega I? You just check which number you are nearest. You have C numbers, right? That's exactly K-mean is doing. If omega I known, you do Ci, it's just average value. That's a quadratic. So in this way, you see Ci is just alternating minimization. But you see, so this is a non-convex problem. So therefore, Ci is you cannot guarantee global. The K-mean you cannot guarantee global minimizer. It mostly depends on the initial value. But this easily observed. You see, the K-mean is just alternating minimization of this one. If you regularize, and then we come to the Mumford-Shah and the CV. I think this is making a lot of things getting more and more closer. There's a lot of models, but in the end, they are not so different. Oh yeah, maybe we need to stop. So tomorrow, I'm going to show you. So here is a discretized, and then we make it continuous. But once I make it continuous here, you can see this is exactly the Chang-Wei. This is exactly the Chang-Wei. The omega 1, omega 2 total variation. So graph cut is minimizing the Chang-Wei model. If you discretize it, that's what they are doing. Yeah. So tomorrow we continue with this one. I think graph card is still very one interesting. I think there are a lot of things maybe we can do related to graph card. Also by observing those different things, it seems they are getting more connected. The different approaches come together. It just there's a lot of interconnections. So we stop here. So tomorrow we continue. Also we go to the continuous card. This is those are also some new things, and we get more multi-phase things. So let's continue tomorrow.
One last question.
Yeah.
Is graph card faster than level sequencing?
In practice, graph card is always very